Hello everyone, and thanks for joining. In this session, we'll take a look at how you can add common art and design interactions to your games using Unity visual scripting instead of traditional code. I'm Alicea, one of Unity's developer advocates for games. And in this session, I'll be walking you through different visual scripting examples for cutscenes, working with animations, UI, and lots more. We're adding this all to Unity's Adventure sample game, so you can follow along and download it at the link down below. Know that this session is tailored for artists, designers, and other creatives who already know the basics of Unity visual scripting, which is also known as Bolt. In case you missed it, it's a new editor feature that enables Unity users of all skill sets to add interactions for games and apps using visual nodes and graphs instead of typing out lines of C# code. If you'd like a recap on the basics, check out our Introducing Bolt session previously released on Unite Now. Before we begin, let's take a look at what exactly we'll create with this demo. We'll first use visual scripting to work with colliders, keyboard input, animations, and Unity Timeline so the player can activate an in-game cutscene. Our second example will quickly show how to take your player into a new scene. Afterwards, we'll activate and animate some UI to indicate interactable areas. Lastly, we'll dive a bit more into UI along with audio and lists to create the game's dialog system. With that, let's get to it. Oftentimes, as an artist or designer, you may find yourself working on something in Editor that you need to test out or activate through coding. This usually means you either have to figure out your own scripts, hunt for an asset that does what you need, or ask and wait for your programmer to implement your request. Now with Unity visual scripting, you can work more independently and quickly in these kinds of situations, and it works with features you'll commonly use, like the animator, shader graph, and much more. Let's review an example of working with in-game cinematics using Unity visual scripting with Unity Timeline. Taking a closer look at our game's cutscene, let's break down what we want our visual scripting graph to accomplish. The cinematic we want to use for this has already been created with Unity Timeline and applied to the CoffeeBot NPC game object in our hierarchy. This timeline gets activated when the player presses the spacebar while standing on the orange trigger zone. Note how the player character positions itself to the correct rotation for the cutscene before the timeline activates. This repositioning is set with visual scripting instead of timeline to help smoothly transition the player into the cutscene no matter where they are standing within our trigger zone area. Let's go ahead and build out the logic for all this in a new Unity visual scripting graph by adding a machine component to the trigger zone game object. There are two types of machines for visual scripting graphs: flow machines and state machines. Flow machines are best used for executing logic at every frame or when an event occurs. State machines are for executing logic when certain user-defined parameters are met and are most often used for setting game object behaviors or AI. Since we want this logic to activate based on a keyboard input event, let's add a flow machine component. We're adding it to the trigger zone object so it can detect the player colliding within its trigger mesh collider. But we'll also need our graph to reference other game objects in our scene. So let's set our graph source as an embed. Using an embed source locks your graph data to the component in order to enable scene references. This will let us access the data we need on other game objects, like the timeline on our CoffeeBot NPC. We'll add a title and description to our flow machine to keep it organized. And let's also click and drag to select these two default graph units and press delete to remove them. Now that we have a fresh slate, let's add the units we need to activate our cutscene. You can create a unit by right-clicking the graph background. We want the cutscene to activate while two specific events are happening: when the player is within the trigger zone's mesh collider and when the player presses the spacebar. This means we'll need an on-trigger state unit to check for the collision. As we can see in the Graph Inspector window, it requires an input and offers two outputs. The input here is asking for the game object that has the trigger collider we want to monitor. Since our graph and trigger mesh collider are both on the trigger zone game object, we can leave the input as self. The green arrow output directs your graph to the next step in your game logic. Lastly, this collider output tells us what object is colliding with our trigger zone. We want to be sure this cutscene only activates when the player character is within the trigger zone, and not when an NPC might be walking by. By adding a GameObject compare tag unit, we can verify it's the player in our trigger zone by comparing the collider output from our onTrigger state unit with the tag name of player. Since our player's tag is set as player, the unit's output boolean will be set as true. The second event we need to be true is that the player has pressed the spacebar. We can easily check this with a single unit, get key down. It will output a boolean as true when the player presses down the spacebar. Now we need a control unit to say, okay, these two conditions are true, so proceed to the next step of logic. For this, we'll add a branch unit, which is basically an if-else statement that directs the logic flow of your graph based on a boolean's value. We have two booleans we're checking though, and the branch unit only has input for one. So let's combine them with an AND unit. Both input booleans need to be true for this unit to set its output boolean as true as well. Since we're now able to verify that both our conditions here are true, let's store this information in a variable that we can use to trigger the actual chain of events that will happen when the cutscene is activated. To do this, we'll navigate to the variables component on our trigger zone game object. This component is automatically created whenever you add a visual scripting machine component to a game object. We'll add in a new variable name which we'll call cutscene activated. We'll set its type to be a boolean and leave its default value unchecked, which means false. Back in our graph, we can add a set variable unit, select the variable and game object we're referencing, cutscene activated itself, and create a boolean literal unit set to true as the variable's assigned value. The logic we need to activate our cutscene steps is now complete. So let's use the graph distribute tools to make our nodes here neater, and also press Ctrl while clicking and dragging to group them together and add a comment about what these nodes accomplish. Moving on to the actual logic steps needed for our cutscene, we first need to verify that our cutscene activated boolean is true. So let's add a branch unit and drag in our variable from the Inspector tab. This will create a unit that outputs the value of our variable. Now the branch unit alone can't trigger a chain of events because it needs to know when it should check the variable. By adding an update event unit, we can tell our branch unit to check during every frame of our game. Once cutscene activated is true, we can rotate the player to the correct position for the cutscene using a set of 4 nodes. A rotate towards unit will calculate what direction and by how many degrees the player character should rotate during each frame. In order to do this calculation, it needs to know the player's current rotation and what its final rotation should be, which we can do with 2 get rotation units. I'll add one using the right-click menu, but I can also click on a unit and press Ctrl-C and Ctrl-V to copy-paste the second one. For the first input, we need to know what rotation we're starting from, which will be the player's. So let's drag the player prefab in our hierarchy into this unit. For the angle the player should face during the cutscene, I set up an empty game object called Player Cutscene Position. Its transform contains the end goal rotational value needed by our rotate towards unit, so we'll drag this game object to our second get rotation unit. The last input, max degrees delta, is basically asking how many degrees it should rotate the player during each update. Let's make it 10. This rotate towards unit gives us a single output, a rotational value called a quaternion, and we need to apply it directly to our player's transform component so we can see the rotation happening in our scene. We can achieve this with a transform set rotation unit by assigning our player as its target and our rotational value to its quaternion input. Once the player character is facing the correct rotation, we want to continue to the next step for activating our cutscene. So we need to add one last branch unit to verify the player's proper rotation. And this time we'll set its input condition with an equal unit. This unit only outputs as true when the value applied to the player from set rotation is equal to the rotation of the player cutscene position object. We can now activate our timeline cinematic, which is as simple as adding a playable director play unit and telling it which game object contains the timeline we want it to play, which is our CoffeeBot NPC. We've now accomplished all the steps to activate our cutscene, so we'll add 2 final units to end this current flow of logic. Let's copy-paste the set variable and boolean literal units we created earlier, but set the boolean unchecked this time to designate cutscene activated as false. Because our condition for this chain of events to run required cutscene activated to be true, Setting it to false will stop the flow of logic and signal the end of our cutscene process. Let's go ahead and test this in play mode. Once we enter the trigger area and press space, we can see the flow of events happen in real time in our visual scripting graph. This is excellent for visualizing how your graph works or to see where things might be going wrong. In our case, we saw our flow execute perfectly, so we're now ready to move on to our next example, scene management. Working on and testing scene transitions is another common creative task that is actually really simple to accomplish using visual scripting. There are 2 scene transition triggers in this project. One to enter the mysterious ATC Corp headquarters, and another to exit back into the marketplace. Both actually run off the same exact graph because for this example, we're setting our flow machine components as macros. Unlike embed graphs, macros are saved as an asset within your Unity project. You won't be able to use scene references with them, but you can apply a macro repeatedly to any game object in your project. This saves a lot of time if there are specific sets of logic you need to use often for your game. We can create a simple scene transition macro with just 5 nodes. Let's start by checking out this scene trigger game object in our hierarchy. It's positioned in front of the ATC Corp doors and contains a box collider trigger that we'll use to activate our logic for this graph. Let's add a flow machine component to this game object and set its source as macro. Click on the New button next to it to create and save a graph asset within your project folders. In the Variables component that also gets generated, be sure to add a variable to hold the name of the Unity scene you want the player to transition to. I'll call mine Exit Scene, set its type to string, and set its value as the name of my second scene, Security Room _ Bolt. Delete the 2 base nodes in your new graph and add an onTriggerEnter event unit to start your logic flow. We'll use a compare tag like we did in the previous example to make sure it's the player activating the trigger, and then use a branch unit to verify the scene trigger and player are colliding. If the branch detects this is true, we'll move our flow along into a Scene Manager Load Scene node. Instead of entering the name of our other scene into this unit, we'll grab the Exit Scene variable from our inspector and plug that into Load Scene instead. Setting it up this way means we can add this graph and Exit Scene variable into other game objects, and we'd only need to change the variable's value to go to a different scene. Let's do this now in our other security room scene so our player can return to the marketplace. Before I open my other scene, I'm going to click the 3 dots on the top right of my variable component and click Copy Component. Now in our other scene, all I need to do is add a new flow machine component, click the field's target icon to select our Scene Manager graph, and select the 3 dots on the Variables component and select Paste Component Values. All we need to do now is set the value for the exit scene to be market _ bolt, and we now have working scene transitions for both scenes. One of the most common questions we've been asked lately about visual scripting is how to use it for working with user interfaces. So let's walk through a basic UI animation example. When the player approaches an interactable object in this scene, a UI box animates above the object and disappears if the player walks away. Since these are clearly defined behaviors that can occur repeatedly in our scene and for multiple game objects, this is a great case for using a state machine macro. Before we begin, let's break down the logic needed for this UI behavior. We'll be working with the ActionBox game object found under the canvas in the hierarchy. If you set the object to active and check the animator or animation windows, you can see it already has preset animations we'll reference in our visual scripting graph. Within the action box, there's also a UI text game object called ActionText. We'll be changing what this text says depending on the interactable object that's being triggered. Be sure to deactivate the ActionBox game object when you're done, as we only want it to be active during certain specific events. Given what we've covered so far, you might wonder why we aren't using an embed graph since we're referencing other objects in our scene. We could successfully use one and set up direct scene references, but we'd have to copy and paste the contents of our embed graph across every object we want to make interactable. Instead of doing all that, we'll store the scene references we want to make into variables so our macro can access them. It takes a few more steps to set this up, but the time you'll save by being able to use a single macro across many objects will be worth it. You can do this with flow machines as well, not just state machines. Let's take a quick look at the game object we'll apply our state machine to, guard interaction. It's actually an empty placeholder game object positioned in front of the security desk. It has a box collider trigger to detect if the player is near the guard, and an audio source component we'll use later for our dialog system. It also contains a child game object called ActionBox POS1, which contains a specific transform position and rotation our graph will use to position the ActionBox UI. We'll also be applying the same state machine to this laser gate, so the security lasers game object is set up in a similar way. It's time to start creating our state machine. Add a new state machine component to the guard interaction game object and press the new button to save a new macro asset to your project files. Give your macro a title and a summary, and delete the default start state within the graph. Right-click on the graph background and select the Create Any State option. This enables the state machine transitions to trigger no matter what state is currently active in our game. Right-click on any state and select Make Transition to set up our first transition and flow state. Click on the flow state and use the graph inspector to name it Activate Action Box. Now let's double-click our transition unit to open it. Inside this unit, you'll find a State Trigger Transition unit. We'll need this to start the logic for our state machine. That said, we do need to indicate what logic needs to occur for this transition to begin, which is the player entering the guard interaction collider area. Just as we did earlier, we'll add an onTriggerEnter, compare tag, and branch units to verify the collision and enable the transition over to our Activate ActionBox state. Click on Guard Interaction at the top left of your flow graph window to return to the main view of your state machine. Double-click the ActionBox state to open it. You'll find 3 default units, but we only need to keep the onEnter state one, which we'll use to activate our logic flow. Once this state is activated, we want to position the UI action box above the activated trigger area. This can be done with the world to screen point unit. It takes the world space positional value of a game object in our scene and turns it into a screen space position we can use for UI placement. To work properly, the unit needs to reference our camera game object, and it also needs to know what world space position to convert. So far, we've only been creating object variables using the variable components on our objects through the inspector. But if we open the variables window, we can see there are a few additional options for variable creation. Let's create a scene variable called camera, set its type to camera, and drag the camera in our hierarchy into its value field. While we're here, there's a couple of other variables we need to create. So next, let's do the same for our action text object and set its type as text. Lastly, we also need a reference to the ActionBox object itself, so add a game object variable called ActionBox and set the aforementioned game object as its value. Since the ActionBox position and text will vary depending on the interactable object the player is near, we'll need to add transform and string variables as well to each game object we'll add this state machine to. Go to the Object tab in the Variables window and add a transform game object called ActionBoxTarget and a string variable called ActionWord. Drag the corresponding placeholder object in your hierarchy into the value for ActionBoxTarget. In this case, ActionBox POS1. Set the value for the ActionWord variable to talk so the player knows what interaction will happen with the guard. Lastly, we'll add an ActionBox active boolean to use later as a branch condition for our dialog system. Now let's get back to our state graph. We now have our camera variable, so let's plug that into our world to screen point unit. We can also add our ActionBox target variable to the graph and connect it to the same unit using a getPosition node. Now the state machine will know what position the UI box should be in. Don't forget to apply this value to the action box using its variable and a setPosition unit. We also need to update the action box's text to display the word we set as our action word. We can do this by adding a setText unit and setting its target to our ActionBox text scene variable and its value to our action word object variable. Now we can set our UI action box to be visible within the scene using a set active unit linked to our action box variable. We'll then link the same variable into an animator set bool unit so we can trigger the preset animations in the object's animator. Through the animator window, we can see the transition for the open animation is activated if our isOpenAnimator boolean is set to true. So we'll enter these same values into our set bool unit. In our last step for this state, we'll add another pair of set object variable and boolean literal units to set our action box active variable as true. We can enter play mode and see our state is now working as the action box appears above the guard. But it's not disappearing as we walk away. We can resolve this with an additional transition and state containing just a few units each. First, let's create another transition from our AnyState unit and call our new state deactivate action box. We'll copy-paste the same units over from our first transition, except we'll swap onTriggerEnter with onTriggerExit in order to activate the next state when our player walks away from an interactable. Now open up our new state and use the onEnter state unit to set the logic flow for 3 additional units: animator set bool, wait, and set active. We'll want to set the isOpen boolean on the action box animator to false to trigger its closing animation. So set its target to our action box variable, its name to isOpen, and its value unchecked as false. The wait unit delays the flow of logic by the number of seconds of your choosing, though we just need to set it to 1 second so we can give the UI closing animation enough time to complete. Once it's done, we can continue our flow into the set active unit where we'll set our action box object as inactive, hiding it from our scene. Finally, we'll add the units needed to set our action box active variable as false. If we enter play mode to test this state, you'll see we get an error related to our wait unit. That's because it can only run within a coroutine, which enables a synchronous logic flow for your graph. You can easily set an event unit as a coroutine by selecting it and checking off coroutine in the graph inspector. Now our state machine is in full working order, and we can add the same state machine macro and corresponding variables to our security lasers game object. For the UI to display with the correct position and text for the laser gate, we'll set the action box target as the action box POS2 game object and set our action word string as scan. Entering play mode, we can see everything works as expected. So now let's move on to our final example, a quick review of how you can use many of the nodes you've learned about in this session to create a UI dialog system. Starting with a new flow machine embed, we'll start with some units to confirm the player is pressing the X key while the action box for the guard is active. We'll use another animator set bool unit to trigger the action box's closing animation, and we'll set the dialog box game object to be active with a set active unit so it can become visible in our scene. Just like the action box, the dialog box has its own opening animation that we can trigger with an animator set bool unit. Now we're ready to work with a few new units to create a very basic dialog system. In order to display multiple lines of text and play multiple audio files, we're going to use lists and a for each loop. Lists are a type of variable we can use in visual scripting as containers that hold collections of data of the same type. We'll add a guard script list of string variable to hold our dialog text, and a guard voices list of audio clip to store the audio clips we want to play while the dialog system is active. Now that we have a way to store these strings and audio clips, how do we use them in our graph? By using a for each loop, our graph can execute a series of nodes for every object within a specified list collection. Let's set the guard script list as our input so we can repeat our needed logic for each line of dialog we have. Using the unit's body flow output, we can link the nodes we'd like to execute for each string in our guard script list. Now we'll add a set text unit to update the dialog box UI text with the current string value. We can grab this value from the for each unit's item output. From there, we can add an audio source play one shot unit to play an audio clip from our guard voices list at random. To create this randomization, we just need to add 3 units. A getObjectVariable unit to reference our guard voices list, a listGetItem unit so we can access one of the clips from this list, and a random range unit that will output a random number we can use to determine the list index or item number we are accessing and using for our play one-shot unit. We'll then add a wait unit with a delay of 3 seconds to give the player time to read the text as it appears and to allow the randomly selected audio clip to play in full. Don't forget to set the onKeyboard input event unit as a coroutine for this wait unit to work. With that, we're all set with the logic we'll execute for each item in our dialog list. Now we just need to add the flow of events that will continue once the for each loop has been completed. Branching out from the for each unit's exit flow, let's add some animator setBool and wait units to trigger and give time for the closing and opening animations of the dialog box and action box UI items, respectively. We'll then add our final unit in this session, a setActive unit to hide the dialog box from our scene once it's animated away. With that, we can enter play mode and see how the dialog UI now runs and updates automatically based on the strings in our guard script list. It will still work even if we add in additional strings to that variable, like I'm doing right now. I kept this example short for the sake of time, but you can absolutely extend or modify a visual scripting dialog system like this to work with files like CSVs or related UI features like TextMesh Pro. To wrap things up, I hope these examples serve as helpful guides and inspiration for ways to use visual scripting for your own game projects. Please do let us know in the comments what other types of visual scripting tutorials and examples you'd like to see. This session covered just a small portion of what you can achieve with Bolt, so let me leave you with some parting resources that can help you discover what else you can accomplish with this feature. Our documentation will serve as your primary resource for information on how Unity visual scripting works, its core concepts, important features, and lots more. The visual scripting templates available on the Unity Asset Store are excellent projects to download and analyze as you're learning visual scripting. You can even use the assets, flow machines, and state machines it contains for your own projects. The new visual scripting section of the Unity forums is a great place to ask questions and engage with fellow Unity visual scripting users. Lastly, you can find a bunch more visual scripting projects to reference and learn from via my Visual Scripting Samples GitHub repo. It contains the project from this session and will be updated over the coming months with even more template projects and tutorials. If you ever have any questions about visual scripting or want to show off something cool you've created, you can also find me over on Twitter as Ashley. Thanks again so much for joining this session. Enjoy the rest of your night now, and happy game making!